Hey all, welcome to Share Trek. This is Raj here, and today I want to revisit Beam 201. I'm actually going to talk about a concept that is generally a problem for most CRISPR companies, and Beam 201 is on hold if you recollect, and we have generally felt that Beam was moving too slow. In today's video, I'm going to try and explore why, and as we are investors, we generally get impatient. Are we really justified to get impatient with Beam, or are there some serious issues generally for the industry? That's what we try to explore in this video. So let's get started. Welcome back, friends. Have you ever seen the complicated wirings in a telephone junction box and wondered how complicated it is? You may have a pair of scissors and other tools, but would be afraid to touch any of the wires as you don't know what would happen. I myself have often looked at the telephone technicians working on junction boxes, and I wonder how they learn about these things. How does my call reach my phone if somebody dials it? Of course, it's not a big mystery for those technicians who are working on it because it's an established science. They know exactly which wire goes where and how the whole system is organized. So they are able to effectively use all the tools that they have at their hand to do the task and to rewire the system. Well, CRISPR-Cas9 gave us scissors, base and prime editing gave us more refined tools, and the genomic sequencing companies gave us genomic sequencers, as well as softwares to review, compare, search, and look for patterns such as tandem repeats, mutations, etc. in the genome. Still, we are looking at something more complex than just the telephone junction box. Nature developed our biology over millions of years, and in the process there are redundancies, vestiges, and some unexplained genetic payload. It will take us longer to understand everything. CRISPR-Cas9 makes double-stranded cuts in the DNA within a gene. This allows error-prone DNA repair and introduces errors in the hope that these will silence the target genes. DNA repair in the cell is understood to be probabilistic, in that in a given DNA cut, it can be repaired in many different ways. What this looks like when applied to a group of cells like T cells for CAR-T therapy or an intact tissue like in a retina is that different cells will contain different edits and not all of them will silence the target genes. This is called mosaicism or genetic impurity, and it is pervasive across all species. This is the first level of complexity. Not considering this would cause unintended effects. Currently, there are no viable solutions to tackle mosaicism at the target site for cell and gene therapy. There is growing understanding that when multiple genes are targeted for silencing simultaneously, it is possible for intervening segments of the genome to shuffle. This in turn can cause unpredictable issues. This phenomenon has in part contributed to FDA placing Beam Therapeutics Beam 201 base editor on hold. In response to this hold, the field has adopted a more rigorous approach to mapping the frequency of any genome shuffling in a manner similar to how off-target editing is now being approached. The draft guidance by the FDA recommends an assessment of genome shuffling and large deletions by robust methodologies. Most CRISPR therapy companies have at least one program focused on next-generation cell therapies. To enhance these therapies, the next-generation cell therapies with regard to persistence, efficiency, and safety, multiple genes need to be silenced within a given cell. Multiplex silencing represents a significant roadblock to CRISPR realizing its full potential in this space. Some examples that I can bring up are the CRISPR edits that are made to CAR-T cells to help them persist longer, evade immune suppression, or be more efficient. It is now recognized that between 3 and 12 gene modifications are necessary to enhance autologous and allogeneic CAR-T therapies respectively. CRISPR results in mosaicism at the target gene, with only a fraction of edits silencing the gene. Importantly, as the number of genes to be silenced are increased, it drastically reduces the probability of getting a cell that contains all the desired edits in it. For example, there are published cases where triple gene silence next generation CAR-T therapies administered to patients contain less than 2% of cells with the desired edits across all 3 genes. The low proportion of multiplexed edited cells presents an enormous manufacturing challenge as investigators have to invest heavily in novel methods to purify out these rare therapeutically relevant cells. So it introduces one more level of refinement. After the edits have been introduced, now you have to check each of those cells to make sure that all the three genes have been edited appropriately, and only those cells have to be progressed further into therapy to the patient. But this is what is causing a lot of problems, and you can't have such an inefficient manufacturing process, because the cost of the therapy will go astronomically high and it will become unaffordable and not feasible. To further complicate the autologous approach, autologous cell therapies where patient-derived T cells themselves, which are used to make CAR T medicines, are compromised. This is due to the T cells being derived from patients who have already received toxic preconditioning chemotherapy regimen. In this setting, multiplex gene editing to generate next-generation CAR T medicines is generally not feasible. On the other hand, if you look at the allogenic approach with healthy donor cells, we have a different problem. Here, the challenge is that often substantially more genes, like around 8 to 12 genes, may need to be silenced to overcome rejection due to the CAR Ts being seen as foreign, which is what we call as immune resistance, or we refer to as graft versus host disease. So from what we have seen, there seems to be multiplex editing ceiling above which it's not possible to silence more genes due to mosaicism. Currently, the multiplex ceiling falls significantly short of 8 to 12 genes that need to be silenced simultaneously. This multiplex ceiling, driven by DNA impurity at the cut side, need to be overcome if the next generation CAR Ts are going to help the market expand from 1.2 billion now to 22 billion in 2031 as predicted. So in my opinion, I think at the most 3 genes being edited could probably help us have a reasonable logistics. And I don't know how many therapies can be created just targeting 3 genes. Until this issue is resolved, only diseases needing 2 to 3 gene corrections will be addressable using the CRISPR tools. Well, friends, I hope this video made some sense, as it is difficult to simplify and present complex genomic concepts as a non-scientist. I think a link in the description that I'm going to leave for you will help you to read the article yourself and draw your own conclusion and do your own further research on the internet trying to understand this issue. But this is one of the many factors that has dogged Beam 201. In conclusion, I would say that we got to be a bit more patient with Beam Therapeutics because of all the challenges that we just saw. This is just a small portion of the hurdles that Beam has to cross through in order to come up with a viable therapy, and it's the same for most of the CRISPR companies. But with regard to Beam, I still think that they are spreading themselves too thin, and the ecosystem is just expanding. So that's the only concern I have. We have to see Beam coming up with some kind of positive development in the next 6 to 12 months in order for the enthusiasm to remain. That's my personal opinion. But of course, just like the telephone junction box that we see, as laypersons, it's very complicated. We don't understand how it works, even if we are given the tools. I think it's a similar situation for even the scientists who are looking at the human genome and trying to understand how all the genes interact with each other, what are the interdependencies, and the complex system is still getting unraveled day by day. And with every new effort, we are finding new challenges, and when we solve those challenges, new ones open up. So it's a long-term journey, and we are in the infant stages of the CRISPR revolution. We got to be patient, and definitely quality of life is going to improve for many people who are suffering from various genetic disorders. Help is coming. It's going to take some time, but it's not hopeless. We can see the light at the end of the tunnel. And already some gene therapies have already been approved, and they are hitting the market. And some of the CAR T therapies have also been in the market for a while. So it's not all doom and gloom, but if you want a really good quality, absolutely reliable, less risky therapy at lower cost, we need to solve a whole lot of issues. And I think Beam is also working on that. So let's give them some time, and let's support the industry overall. So that's what I would like to end this video with. Friends, if you like this video, please press a like out there. And if you're not yet subscribed, please subscribe and help me grow this channel. Thanks and have a great day. Bye for now.